Professor Hope will give a series of lecture on homological invariants of sequence of symbolic powers of monomial ideal. So last week, you heard Professor Taiha talking about the symbolic powers and containment problems in the context of the containment problem and some inequalities, what he was discussing. But this time, Professor Hope will highlight uh, the symbolic power for the monomial ideal cases. And these kind of topics are very, very important when we talk about the blow up of varieties in the context of algebraic geometry. And one of the central problem in regarding to the symbolic power is the regularity of the monomial ideals. So all the lectures of Professor Hope will be particularly directed toward the regularity of ideals associated with the symbolic powers. So over to you, Hope. Please share your screen. Let's see. Let's welcome Professor Hope.
Okay. Thank you very much.
Yeah, we can see your screen.
Okay, so first of all, I would like to thank the organizer for giving me a chance to talk here in this nice school. Okay, so yes, I hope I could try. I could travel to Lahore. That could be my second time in Lahore. So the first time was in 2018, yes, and it was also in a CIMPA School. And yes, I visited Lahore. Yes, so it's very nice, and if not for this present crisis, not for the pandemic, then I think now I would be in Lahore. Okay, but on the other hand, now we have this possibility to meet online, and so let's see if I can. Okay, we can get to know something about powers of idea and symbolic powers of ideas. So I plan to talk mainly about that instead of regularity because the problem about regularity, I spend some time on it, but we do not have good results as in that case. So we start first with the classical problem on that of ordinary powers, and then we will move on to that of symbolic powers. Yeah. So so first, can you hear me well?
Yes, yeah, we can hear you. Okay. Just one request. If you can place your mic a little bit farther.
Okay.
Now it's okay. Now it's okay. Yeah.
Okay. So first, let us recall a few things about that and powers of ideas. So this is to fix the notation. Yeah. So we start with we have a field K, and we look at a standard graded polynomial ring R over K in variables x1 up to xd. Yeah. Okay, and M with a greatest maximal idea of R. Okay, we will mainly talk about ideas, but so it is convenient to introduce also M finally generated R module. Yeah? So I will be the idea that we will mostly talk about. I is another homogeneous idea in this polynomial ring. So so what is a depth? So first we say that a sequence of homogeneous elements y1 up to yn is a regular M sequence, or to simplify, just an M sequence. Okay? If y1 is a non-zero divisor on M, so if I mean the multiplication with y1 is an injection and so on, yi is a non-zero divisor on M divided by y1 up to yi minus 1 times M for oi from 2 to n. Yeah? And another condition that we require for regular sequences is that M modulo y1 up to yn times M is non-zero. So actually the notion of regular sequences is very natural, and it is important in algebra and geometry, because with this you can do induction. Is or in geometry you have various Bettini type theorem, and what you essentially do is you start with some algebraic variety, and you want to cut it down by some hyperplane section to get a subset of smaller dimension. You want to preserve some good property, or you want to have good control of the various invariant, like the dimension or the degree of the hyperplane section. And so this is one situation where you have good control when you cut down by regular elements in hyperplane section corresponding to regular elements, then you can control many things. Okay, so that's why we are looking at this. Basic example is you take M equal to the polynomial ring, then you get that x1 up to xn is a regular R sequence, or On from 1 to B. This first easiest example. Or you can take, now we look at polynomial ring in 3 variables, x, y, z, and M to be R modulo x times y times z. And then you can check that x minus y and y minus z is an M sequence. Okay. And then we say an M sequence consisting of homogeneous element in M is a maximal M sequence if you cannot extend it to a longer M sequence. Yeah. Basic result about a regular sequence is any two maximal M sequence have the same length. Yeah? So any maximal M sequence in a homogeneous idea N has the same length given by this formula. You see, the formula is infimum of I, such as the x module of R mod M with respect to capital M is non-zero. You see, it does not depend on any choice of our regular sequence. maximal
Excuse me.
sequence. Yeah.
Uh, uh, this condition of homogeneity is mandatory here. We can have a regular sequence without having the homogeneity.
Yeah, actually, you don't need homogeneity here also. Yeah, but yes, this is just for convenience of discussion. Yes.
Okay. And here, definitely, when we are considering M is with the same grading, which is being induced through R.
Mm-hmm. Yes, yes, with the standard
Yeah,
weighting.
graded
Mm.
module. Yeah, yeah. Okay,
Mm.
okay.
Ask him to
Mm.
tell us what is extra.
Kaun
Yes,
sa?
so,
So,
yeah,
okay.
this is not very important to our discussion. So, but this is the X module. So it uh, is a derived function of the home function. Yeah? But actually, I just need this formula so that you see that uh, also our discussion of the regular sequence involves the elements y1 up to yn, the length, yeah, the length itself, the length of the maximal sequence depends. You see, it depends only on m, yeah, on the module m, yeah, not
Uh,
on
uh,
the
uh,
regular
uh,
sequence.
Professor Hope, there is a
Yeah.
question. Can you define formally what is the X module?
Uh, yeah. Okay. Maybe. I mean, one way to compute this, yeah, to compute this, for example, is that uh, you start with a free resolution of R mod n. Yeah, you take had to be a free resolution of this R mod n, right? As an R module, yeah, and then you form then you can form the complex harm of f to n. Yeah, you will have a complex like this, but you have to be careful about the direction of the maps. Yeah. So, for example, if our resolution f look like this, then this sequence will start with actually it look like this. Yeah, from f0 and to uh, of f1 and so on. Yeah. So the direction of the map goes like this. And if you and if you do this, then generally this complex I denoted by hom fm is generally not exact. So you have the homology can be non-zero and better the cohomology. Yeah? And if you compute the ith cohomology of hom fm, then you get this module, yeah? X of mod m to n. Yeah? But okay, if you want to read more, then you can take any book on homological algebra, like I don't know, maybe the book of Rodman, an introduction to homological algebra, and then X is discussed extensively there in any book in homological algebra. So, but as I said, in our case, we only need to know that the length and the maximal m sequence uh, is an invariant of the module m itself, and we call it the depth of m. And okay, another nice thing is that the depth is related to various other things, and you can compute it in other way, not usually using this formula in the theorem of Reeves. So, for example, we have the following properties: the depth equal to depth of capital M equal to 0 if only if the maximum idea M is an associated prime of M, and that is to say, the maximum idea M is the annihilator of some element X in capital M. Or for arbitrary prime idea P, then P belongs to associated prime of M is equivalent to M localized at P at depth 0. So this we see as a module over the localization ring P. And you have good control by dividing two regular elements. So if X is M regular, then depth of M modulo XM equal to depth of M minus 1. Similarly, for dimension and some other invariants of M, you also have nice relations like this between the constant and the original thing. And that is bounded above by dimension, by the crew dimension. So any P associated prime of M, we have that the depth of M is at most dimension of R mod P, and dimension R mod P is not larger than dimension of M. Or that P is also in other ways. So, for example, we have the Osler-Buchsbaum formula relating the depth and a number you have seen in the lecture of Professor Sarah Faridi. Yeah? So the depth of M equal to the dimension of R minus the positive dimension of M as an R module. And here we use implicitly the fact that R is a regular ring, so M has finite positive dimension over R. Or the depth also can be computed via the so-called local homology of M. Yeah? We support as the maximum idea. So depth is a minimal number I, such as the local homology HIM of capital M is non-zero. We will come back to this local homology later. Okay, so that is a basic invariant, and now we talk about depth of powers. Yeah.
Yeah. Please go back to the Grothendieck's. Yeah, here.
Yes.
Because everything is written, probably a little bit speed issues there. Yeah.
Okay.
May you
yes.
explain again the Grothendieck's here?
Yeah. I mean, so the point is, with local homology, you can get many other information. Yeah? For example, the dimension you can also get from the local homology, or the regularity you can also get from the local homology. Yeah? Yes, so local homology is a basic invariant. And, so the depth is, in this sense, you see that the depth is also related to a basic set of invariants of M. Yeah?
Yeah, in fact, none of the participant has in this school. It wasn't introduced. Local cohomology. Can you again write few lines about what is the local cohomology for the participants?
Yeah. So maybe let me say quickly that you can write down a very explicit complex to compute the local cohomology, and it is called the check complex. Yeah. And yes, so for example, for for our ring R, for example. For our ring R, you can form the so-called check complex of R, and it starts like this. This I will come back later. But okay, the check complex look like this. So this mean the R sub xi, yeah. So not R times. So x of this R sub xi is the localization of R at xi, and so we have a complex like this with the map essentially given by localization, yeah, with some suitable sign, and this is called the check complex of R, and the local cohomology are precisely the cohomology of this check complex. Yeah. But don't worry, I will come back to this later. This is just to tell you that that is somehow a basic invariant to consider. Yeah. So now we talk about depth of powers of ideas. Yeah.
Probably it is better to write a good reference for the participant from where they can read the formal definition of local cohomology in the context of check complex.
Yes. Yes. So you can look at the book of Bruns and Hesselhoff. The book for Macaulay Rings.
Thank you.
Yes, and it is in chapter 3 of this. You can look at chapter 3 of Bruns and Hesselhoff, and it will find local cohomology and Grothendieck's theorem. Okay, then we will talk about theorem of Brodmann about depth of powers. So so in lectures of Pi, you have heard about ordinary and symbolic powers, right? So this is a nice thing about depth of ordinary powers. Yeah? So we start with ordinary powers first, and then we will talk about symbolic powers later. So the nice thing is that you start with the idea I, and you look at the ordinary powers of I, then many invariants become nice in the long run. So for example, the associated prime of the powers of I will be constant set, and the depth will be a constant number for large enough n. And in fact, there's also an upper bound for the limiting depth, and that limiting depth of R modulo I power n when n large is bound above by the dimension of R minus the so-called analytic spread of I. So the analytic spread is just first you take the Rees algebra. This is the RI that I'm written here is called the Rees algebra of I, and yes, so
yeah,
it is.
Yeah, excuse me.
Yes.
In this result of Brodmann, is there any condition on the ring? Ring need to be local, or it is true for every ring?
Yes. So I'm restricting myself a little bit here. I start with a polynomial ring, but in fact in the result of Brodmann, you can start with just any local ring, not necessarily regular.
Yeah, okay.
And
Local
there's
ring,
also a version where you can start with any Noetherian ring. Instead of that, you look at correct, and there's a similar and more general result for the grade. Yeah.
Okay, I have one more question, Professor. So,
Yeah.
so in the theorem of Boltzmann, where you say that there exists some n, so there, I mean, is there any name for such a n? Like if we take it, the starting point, the smallest n for which we are having this condition.
Yes. It is a very well studied problem here. So for example, the smallest number n, so that you have this equality is called I think it is called the stabilization index for us, and this is similarly called the stabilization index for that. And Herzog and his co-authors have many papers on these invariants. Yeah? So you can.
Okay. Yeah.
So this is called stabilizing index. You say stabilizing index.
Yeah. Stabilization index. I'm not very sure, but you can check for stabilization index for us and stabilization index for that, and you should find many papers on that. So usually it is denoted by this for the second invariant, and I start for the first invariant. Yeah.
But aren't these two numbers same?
No. They can be different. I just say that it exists. Yeah, but the smallest number such that these equalities how may be different. Yeah.
Okay. Thank you.
You're welcome. So yes, so this is called the Riesz algebra. You take the algebra generated by R and R with and you add I times T. So it is a standard vector algebra over R with the I component being I to the I, T to the I. Yeah? And you take the obvious multiplication like this. Yeah? It is contained in I to the I plus A, T to I plus A. Then you get, yes.
What did you name it? The L of I is called, I forgot it.
Yeah, so this is the Riesz algebra of I. Yeah?
No. L of I in the above.
Okay, sorry. Yeah, you mean this the analytic spread? Yeah.
Analytic spread. Yeah.
Yes. And this is the Riesz algebra or the blow-up algebra. Yeah? So yes, so the Riesz algebra actually is what is acting what is controlling everything here. So in the proof of Boltzmann's theorem, you see that mainly we use the fact that it is this Riesz algebra is a Noetherian ring, and it is standard rated. Yes, these are the most two most important properties of the Riesz algebra that give rise to such result as this theorem of Boltzmann here. Okay, and there are many work on the eventual behaviors of that or this limit. Yeah. So, for example, there's for S ideas, so you can take a graph and you form the S idea of that graph. Yeah, generated by all the product of two adjacent vertices. Then you get something called an S idea, and there's a nice result due to Trần Nam Trung that determine both this A stat, yeah, no, sorry, is the D stat, and the limiting depth of the power of such an S idea. Yeah. So, for example, you can prove that the limiting depth for power of S ideas is equal to the number of bipartite connected components of G. Yeah. And okay, the stabilization index is at least very roughly it is smaller than the number of vertices of this graph. So it's very small bar.
This is
Okay.
true for all kind of graph. A simple
Yes.
graph, all
Yes.
kind of simple graph, I think.
Yes, exactly.
And if the graph is disconnected, still the result holds.
Whether it is connected or not, yeah, you always have this formula. The lim is equal to the lim that is equal to the number of bipartite connected components. So if the graph is connected but not bipartite, then the lim that is 0. For example.
And when we are taking, okay, so this thing can be computed only by looking at the graph. So what will be
Yes,
this limit appearing? This is a kind of definition, or this is the result?
that is a reason. Right? So this you can always start as in Brodmann theorem. You can start with any idea, and then you know that there is this limit exists. But what is it? Yeah, and then in the case turns out that in the case of S idea, you can determine the limit in terms of the graph. Yeah,
Thank you.
yeah, you're welcome. So, so now we recall the symbolic powers from Thai's lecture. Yeah, so recall that the n symbolic power of I is, you just start with all the associated prime of R mod I, and you raise I to the power n, localize at P, and then pull back to R. So these are ideas in R, and you take their intersection, then you get an idea in R called the n symbolic power of I. Yeah. Okay. So our main question will be this: we want to see whether the theorem of Brodmann is also true if we replace ordinary by symbolic powers. Yeah. So question is whether this sequence is eventually constant. And okay, there are some reasons for this question. So, for example, you can check that the set of associated prime of symbolic powers is also eventually constant, just like in Part.1 of Brodmann's theorem. So,
Excuse me.
there's
This is not true in general. Um, yeah.
yes,
Associated prime of the symbolic power increases with the power of n, or it remains the same.
I mean, there are, with this definition of associated prime, is the associated prime of symbolic powers may vary from the beginning. Yeah? There's another definition of symbolic power using minimal primes. With this very definition, then the associated prime of symbolic powers do not change. Yeah? But so that we don't introduce two different notion for symbolic powers, I also use this definition.
According to the second definition, yeah. According to the second definition, I think in that case is the power, the symbolic power. If we keep on changing, the associated prime will remain always the same, right? The other definition.
Yes. With the second definition, then the associated prime of the so-called mean symbolic power, yeah, is always equal to the minimal primes of I. Yeah. But what we are talking about here is the so-called associated symbolic powers, yeah, and it is different.
Okay. Okay.
So yes, so in the end, we will see that the answer to this question is not But there are also very nice results related to this. So, for example, it is true if I is a square-free monomial ID, this is due to Raj and Namjoon, Kimura and Tera. They prove that if I is a square-free monomial ID, then this limit exists. Yeah, and they can also compute the limit explicitly. It is given by this formula d times d minus the so-called symbolic analytic stress. Okay, so this question will be our main goal here. And so first we will talk about symbolic powers, and then today we will also talk about a tool to study this question on monomial ideas, the so-called Takayama formula. So let me talk quickly about symbolic powers, monomial ideas. So
hope can you
yes.
can you explain a bit of the last Terai result? Yeah. Okay. Yeah.
This one.
Yeah. This one. Yeah.
Yes. So actually, so the main difference between ordinary and symbolic power is that the symbolic rays and zebra. Yeah? This is called the symbolic rays and zebra. So the main difficulty is this guy is generally not notarial. It is not notarial in general. And so it is usually very difficult to study sequence of symbolic powers. But in the case of monomial ideas, and this guy is not variant. And in the case of square-free monomial ideas, this guy is even not variant when quite Macaulay. And so that is one of the main reasons why it is true.
And how the above result of Professor Chung, yeah, it didn't work here because every scale-free ideal is related to a graph, and one can compute this limit through the combinatorial definition, combinatorial result, the connected component bipartite components.
You mean in the case I is an S idea?
Yeah, if I is a scare-free idea, okay, that is a particular case. This is more general. This is more general.
Yes, it is more general, exactly.
Yeah.
And okay, the previous result is for ordinary power. Yeah? This result is for ordinary power. And this result is for symbolic power. Yeah? This is more difficult.
Yeah, I understand. Thank you.
So to simplify things, we will mainly work with unmixed ideas. So I is called unmixed if the associated prime of I is the same as the minimal primes. And this will be the case for primary idea or prime ideas or radical ideas. They are all unmixed. But this is an example of an idea which is not radical, but it is also unmixed. X squared y times z in ax, y, z. Okay. Now, how can we compute?
Yeah. Hope may you keep your speed a bit slow. Again, starting with the symbolic power of monomial ideals. I think the people is noting down at the moment.
Okay.
I know.
Okay, so I mean, this is unmixed because you can easily check that x squared y z equal to this intersection x squared y intersect with x squared z. And it is an irredundant primary decomposition. And so if you look at the associated prime of I, and this is the usual notation for associated prime of I mod I. Yeah. And you see from here that the associated prime of I is x, y, and x, z. And so these are also precisely the minimal primes of I. Yeah. And so this idea I is unmixed. So and we want to prove simple result like this. So let I be an unmixed idea, and I equal to Q1 intersect with QS is an irredundant primary decomposition of I. And then the T symbolic power of I equal to the intersection of the T symbolic power of Q1 up to QS. Yeah. So in particular, if Qi to the T to the ordinary power T is primary for OI from 1 to S and for OT, then at least you can compute the T symbolic power of I as this intersection of some ordinary powers. So maybe I will skip this proof. I can send you.
Now we are going to use this definition of the symbolic power now on.
Yes, so definition is always the above definition that I gave you.
Again, this lemma 2.1 statement.
Also in this lemma 2.1 problem.
Yeah.
Exactly.
And for all t greater or equal.
Yes. And I will send you the files. So the proof is written here. It is not that difficult. So maybe it's better that you study it on your own. We move to something more interesting. So still we want to give a formula.
Yes. Here you are taking the power of QIs as a symbolic power?
Exactly.
Or
yes.
the ordinary power in the lemma 2.1?
In the first formula, it is symbolic power. Yeah.
Yeah.
And in the second formula, it is ordinary power. But note that in order to have the second formula, we need this assumption. Yeah? It is a rather strong assumption. Usually, if you have a primary idea and if you raise to some power, then it need not be a primary idea anymore. Yeah? Even if you start with a prime idea and you raise to some power, then maybe you do not get a primary idea. But my point is that this lemma is true if I is a monomial idea. Yeah? That's why I write down here. And now I come to that portion. So you can for monomial ideas, everything about prime and primary is very simple. So a monomial idea is prime if only if it is generated by a set of variables. And the idea I is primary if only if you have a subset I1 up to ij of the index 1 up to d, such that I is generated by powers of x, y, I1 up to ij, and monomials involving only of those variables x, y1 up to x, yj. And from the second statement, you easily get the third statement that if I is the primary monomial idea, then all the powers of I are also primary. And so you see that's this assumption in lemma 2.1 will be satisfied if you start with a monomial idea. Yeah? So if I is now a monomial idea in a polynomial ring, then you can look at an redundant primary decomposition apply into primary monomial ideas. And because X of the Qi is a primary monomial idea, all of their powers are also primary. And so you get this rather simple formula for the symbolic powers of a monomial idea. Yeah? And that is exactly what lemma 2.3 is saying. Yeah? We have an unmixed monomial idea. We take an irredundant primary decomposition into intersection of primary monomial ideas. Then from that a primary decomposition, you get all the symbolic powers, at least in the intersection of it.
This result only true for unmixed case. What happened in the mixed case?
Yes, it's a good question. There's also a version of this for the mixed case, but instead of taking redundant primary decomposition, you should take the primary decomposition, but then you group all the components with whose radical is contained in a maximal associated prime. Okay, it is then you will get some similar formula similar to this. Yeah? So so the mixed case is more involved because in the mixed case, so the Qi that you are looking at here need not be primary. Yeah? It is X of the Qi in the mixed case will be an intersection of primary idea whose radical is contained in some maximal associated prime of I. So you can have a look at it in the paper Symbolic Powers of Monomial Ideas due to and some of his this is a paper due to Cooper and I and some other people. Just
by
a
whom?
few
By
years.
whom? By
Yeah, I don't know all. I don't remember all the name, but there's Susan Cooper and Tai Ha, and I think and Andrew Hopper, some former student of. Yeah, I'm not sure. Maybe Sarah or someone. But yes, there's a formula for similar to 2.3 for mixed monomial idea. Yeah.
So
usually
in
yes.
Usually in mixed case, which kind of containment one obtain? In the above case, so I symbolic T is usually contained in the primary components power T, or the primary components is
Yes,
contained in
so you always have this
this.
containment.
Yeah, okay. For
Mm.
unmixed case, this is true.
Yes.
Sorry, for mixed case, this is true, but the other side might not be true. This is what you mean?
Yes, so
In the mixed case.
in the mixed case, it need not be an equality. Yes, you only have containment. You also have an equality like this, but you have to be careful what is the Q1 and what is the QS. Yeah? You have to change the definition a little bit. Okay, and so the proof of 2.3, you just use 1.1 and 2.1 and 2.2. Yeah? And here I note that you can also use similar method to get symbolic powers of idea points. Yeah? It's also satisfy the condition of 2.1. Okay, but I think I will skip that. And here you can, maybe we can do this in the tutorial. And look at this monomial idea generated by x, y, x, z, y, z. it is the S idea of a triangle. Yeah? And we can try to compute the symbolic powers of this idea I. Okay.
In fact, primary decomposition was not properly introduced, but this example is really good in order to just elaborate the participant how the primary decomposition is coming through the graph. May you please a little bit elaborate?
Yes. So usually we will start with ideas that have easy to
just explain this
primary
primary
decomposition
decomposition through the graph.
Yes, it is a special case. So, but in general, for monomial ideas, there is a easy way to decompose monomial ideas. Yeah. By primary decomposition of monomial ideas is an easy problem. You can also look in rules herself, for example, to get the information. Or in the book of Herzog and Hebe on monomial ideas. Yeah. If you want to know more about information about monomial ideas, you can look in this book. So now we introduce a tool to work with that of monomial ideas, and that is called the Takayama formula. So we start with a polynomial ring R again, yeah, and now I will only be a monomial idea, not a general homogeneous idea. So yes, so the local homology I wrote I get the notation before, and here is how you can compute it. Yeah, so we have this so-called check complex. Yeah. So it start like this. So it is R, and then you take R localized at the xi. Yeah, xi are the variables. Yeah. And it takes a direct sum, and then you take the direct sum of the localization of R as xi times xj. Yeah, where R is smaller than z, and they are between 1 and b. So that is in the zero degrees. It is in the first degree, second degree, and so this is in the nth degree. Yeah. These are homological positions. Yeah. And okay, and from so this is C I, and this is C0, C1, C2, and this is CD. Yeah. And you have a map from CS to CS plus 1 given like this. So it is given on the components. Yeah? If you have localized at xi1 xis, and here on CS plus 1, you have localized at j1 times xjs plus 1. Then the map from this component of CS to this component of CS plus 1 is this minus 1 to the t minus 1 times this is the natural map, the natural localization map. If this set I1 up to IS is one element less than this set Z1 up to JS plus 1, yeah, you throw away JT from Z1 up to JS plus 1, and then you get this I1 up to IS. Then in that case, you define the map from here to be minus 1 to the t minus 1. So t is the index that you are throwing away. and times the localization map. Yeah? So this element is this element times something, so you can localize. Yeah. And otherwise, if in this x y1 up to y I1 up to is not one element less than z1 up to zs plus 1, then we declare that it is a zero map. And with this notation, you can check that z is really complex. Yeah? So d square equal to 0. It is called the check complex. And
by cohomology, you mean the
yes,
homology of the complex?
yes,
For the participant.
Yes, yes. So there is a bad notation. Actually, I should denote it in this way. Yes, it's more traditional to write as the index above. Yeah. Yeah, so by taking the cohomology of this complex, and we get the local cohomology. So more precisely, you take the check complex and tensor product with I mod I. And this is again a complex of R module or a co-complex. And if you take the cohomology of that co-complex, then you get this so-called local cohomology R mod R. And as I said, there is a result also where you also find in rules in sub chapter 3. Yeah. But we don't really need to know the proof here. We will need to know that in the end, we will need to know that such a formula exists. And so the nice thing is that in this case, everything is multi-graded. You can give it a multi-grading such as degree of xi equal to ei. Ei is the I, the basis vector of n to the d. And with this multi-grading I and R mod I are multi-graded, and you can check that the check complex is also multi-graded, because here I only localize at multi-graded elements. So I get multi-graded complex, and so the cohomology that I get is also multi-graded. And so in the end, I can compute the Z is multi-graded elements. So for each element of A in Z to the D, I have a K module, which is the A component of this multi-graded module. And the Takayama formulas give you exactly the dimension for this A module. So essentially, with the Takayama formula, you know all the local homology of a quotient I mod I, where I is a monomial idea. And okay, I quickly mentioned a few notations before we finish. So for a vector A in Z to D with the component being A1 up to A, I said x to the power A is this product x1 to the AN1 and xd to the AD. So it's not necessarily an element in R, but it is in the quotient ring of R, right? Quotient field. And I denote by GA is a set of negative components of A. So all the I such that I is negative. So it is a subset of the set from 1 to D. And for XF subset of D, I denote by RF the it is exactly the localization of R as the product of the variables in F. Yeah. So if you invert all the elements in Xi, where I is in F, then you have this ring RF. And I define delta A of I to be this set of all the difference F minus GA where VA is now VA is the negative support of A, and we require that F contains GA and F is containing B, and such that x to the A, this element is not containing I times RF. Yes, note that both of these belong to the quotient phi of R, right? So you can compare them. And this delta A of I is called the degree complex of I with respect to A. And we can easily check that it is really a simply a complex on B. So this, with this condition, if XA is not containing I times R localized at F, then it is also not containing I localized at a smaller set than F, localized at a subset of F. Yeah? So that's why this guy is closed under taking subset, namely it is simply so complex. And the Takayama formula tells you this. Yeah?
Professor Hope, can we start this Nakayama lemma in the next maybe talk, because now we have to take some questions.
Okay, yes. So
okay, is there any question?
Yes, so I agree.
Sure.
Yes.
No.
So we will move on. This maybe.
Maybe you can explain these things in today's tutorial with some examples.
Yes. Yes. Exactly.
Sure.
Yes.
Yeah. Maybe Nakayama lemma as well.
Nakayama. Yes.
So
yes.
There are some questions.
I have two questions regarding regular sequence that you defined in the starting of your talk. The first one is like you considered a graded polynomial ring, which is indeed a local ring. So I want to know, like, is it necessary to consider a local ring, or we can define regular sequence without a local ring?
Yes. Yeah. Actually, usually in the books, you don't even need local rings. Yeah? You can define. This definition works equally well if you start with just any ring, yeah? Any commutative ring. Yes.
Okay, thank you. The second question is about the ordering of this sequence. So it seems like if we change the order, it may not be regular. So is it true or not?
Yeah, in general, if you change the order, then you can get another sequence which is not regular. Yeah. But I mean, we are working with a standard graded with a graded case. If you work with the graded case or the local case and everything is fine, you can change the order elements in a regular sequence. Yeah.
Okay, so for any ring, when we define, we need to write it as an ordered sequence. Otherwise, in this case, particularly it is fine, right?
Yes, exactly. Yes.
Okay, thank you.
Thank you.
Is there any other question? Yeah, there is one.
If M is finite, R module and I contained in R is an ideal, then the depth of M in R is the supremum of the regular sequences in I. Then how can we link this definition with the definition of yours?
So
if M is finitely generated R module and I is an ideal in R, then depth of M in I is the supremum of the regular sequences in I. So my question is that how can we link this definition with the yours that you write in the start?
okay, yes. So yes, so there's also the notion of depth of M with respect to an idea I, yeah, or grade of M with respect to an idea I. And so what I wrote down as a depth of M is exactly the depth of M with respect to the maximum idea of the ring. Yeah. So yes, I think that is the relation.
Okay. Any other question from the audience?
Yes, it's not a question, it's a request. So are we doing, I mean, in the tutorial, um, can we do like how to construct these degree complexes, which is talking about? I mean,
Check
Okay,
complexes?
yes.
yeah, how can we construct these if we need to compute it by hand? How can we do this? It will
Yes,
give us a
okay.
better understanding of the definition as well.
Yes, yes. Actually, my last part of the talk was about some example, yeah, where we compute the degree complex.
So, Hope, are you coming in the tutorial session at 2:30?
Yes, yes.
So in the tutorial session, what are the plans for the audience so that they can do some practicing of some notion which is being introduced?
I
So
will,
what is the plan for tutorial?
So the plan is first I finish the Takayama formula, and then I move on to example about that of ordinary and symbolic powers of S idea, and also example of the degree complex construction. Yeah.
Okay, okay. And they will, so are you planning to build some check complexes and computing the cohomologies too?
If we have time, but I don't think we really need to work with the check complex, because yes, it is only to convince you that the local homology of a monomial ideas is multi-graded. Yeah, that is the purpose of introducing the check complex. You don't really have to compute that.
Okay, okay.
Mhm.
Okay. If is there any other question or remark? Hope there is a remark. If it is possible that in your lecture you write on side by side so that we can follow you, because there are lots of details which are already written and you explain really well, but definitely noting it down is difficult for us along with following what you are explaining. Will it be possible that you write and explain at the same time for the next lectures?
Okay, okay. I will try. Yeah.
Yeah.
On
Thank
my.
you, thank you, because it is more convenient for everyone.
Okay.
Because there are too many details. Definitely, this is your first lecture with the keywords, and if we don't understand the keywords properly, then definitely a follow-up lecture is going to be difficult to follow for all the participants.
Okay. Okay.
Okay,
I will
thank
try.
you.
Yes.
Thank you. Thank you, Hope. Thank you very much. Let's give applause to